this video in our Chemistry of the P-Block series, we're going to be looking at boron nitride. So this is a compound obviously made of boron and nitrogen, and it tends to feature heavily in the exam questions on this topic. So we're going to spend a little bit of time now looking at this structure and hopefully getting you to understand how the atoms of boron and nitrogen are bonded together. So, this is a giant covalent structure. Empirical formula is Bn, so the same number of borons and there are nitrogens, and it comes in two allotropic forms, two forms of boron nitride, what we refer to as hexagonal boron nitride and also cubic boron nitride. Now, as you can see these two 3D structures floating around in front of you here, hopefully you are reminded of a structure from GCSE. Hopefully you are reminded here of this hexagonal boron nitride. You can see is made up of these flat layers. So I just pause that for a second there. These flat layers, the pinky toned atoms are the borons, the blues, the nitrogens, and we get these completely flat layered structure. Now this hopefully should remind you of graphite from your work at GCSE and Year 12. And in fact, hexagonal boron nitride is sometimes called white graphite, and just like graphite, is a slippery material. On the other hand, cubic boron nitride has got a much more diamond-like structure. Each of the boron atoms, again shown here in pink, are bonded to 4 nitrogen atoms, and each nitrogen atom, difficult to see here in this structure, is bonded then to 4 boron atoms. So if we can pause that again, maybe we can find a point where that's a little bit more visible. Again, in the middle here, it's very difficult to see where the nitrogens are bonded to the borons. Either way, this is very much a diamond-like structure, and just like diamond, it's a very hard and tough material, second only in fact to diamond in its hardness. So we're going to take a look at both of these structures now, and we're going to compare them to graphite and to diamond. Before I do that, however, let's just think of why they're similar to carbon. So just going to look at carbon structures. So if we think of carbon as an atom, then carbon is element number 6 in the periodic table, and its simple electron structure would be 2, 4. So if we take a couple of carbon atoms and think, okay, we'll bond these together, 2 and 4 there as well, then the total number of electrons they're going to be bonding here would come to 8. Okay, and obviously then we'd have each carbon would have another 3 bonds, each carbon forming 4 bonds each. Now, when we think about boron nitride, so boron is element number 5 in the periodic table, so that's 2, 3. So boron is capable of forming 3 covalent bonds in that situation. And then nitrogen is element number 7 with the electron structure of 2, 5. And nitrogen is capable of forming 3 covalent bonds as well. And it also has a lone pair of electrons. So here then, the total number of electrons in the outer shells again comes to 8. And so, just as we saw with carbon, we have 8 electrons involved in bonding. We have 8 electrons involved in bonding with boron nitride also. We would say that boron nitride and graphite are isoelectronic to each other. That is, they have the same number of bonding electrons. So as a result, we tend to get structures which are very similar to each other. That's why we get this graphitic-like boron nitride and this diamond-like boron nitride, just as we do with carbon. Okay, so if we move on now then and start looking at these structures in detail, we'll have a look at this cubic boron nitride first of all. So here's a sort of zoomed in version, and hopefully you can see the bonding a little bit more clearly now. So here are the borons in this sort of pinky tone, and they're bonded to 4 nitrogen atoms. And then if we have a look at this nitrogen atom here, for instance, you can see it's got 1, 2, 3, again, there'd be 4 bonds to boron atoms. So each atom forms 4 bonds in a tetrahedral-like structure, and the bond angle here, if you were to measure it, would be 109.5. This is exactly what we have in diamond, where each carbon atom is bonded to 4 others, and you get this tetrahedral structure with a 109.5 bond angle. Now, this is where things change a little bit here, and I'm putting my own spin on this to a certain extent, so bear with me here. So the blue bonds here, I'm referring to as standard covalent bonds, okay? The red bond I've indicated here is also a covalent bond, but it's a coordinate bond. Now, you don't necessarily see this being mentioned in textbooks and websites, but I'm just doing this so it makes it easier for me to keep a tab on what's going on here in terms of the electrons. Because if you think about it, and I might be going into this a little bit too deeply, but if you think about this, then boron is capable of forming, as we mentioned a second ago, boron is capable of forming 3 covalent bonds with its 3 outer electrons. Whereas nitrogen is also capable of forming 3 covalent bonds, but it has a lone pair. Now, in this diamond-like structure of cubic boron nitride, we require the boron to form 4 covalent bonds, and it can only do that if nitrogen decides to coordinate its lone pair of electrons to the boron. So the only way we can form 4 covalent bonds with boron is to make sure that there's a coordinates bond. The 4th bond has to be a coordinates bond with both electrons coming from nitrogen. So that's why I've shown these bonds in red, even though once they're formed, they're as strong as any other covalent bond. These are formed by the lone pair of electrons on the nitrogen coordinating to the empty p orbital on the boron. And so in my mind, I can keep a track of where the electrons are doing by showing this, but I don't think you need to necessarily show that in an exam. Okay, the resulting structure then, 4 covalent bonds, whether they're coordinates bonds or not, is going to be a really hard and tough structure, just like diamond. In fact, cubic boron nitride is second only to diamond in its hardness. Very unreactive, as you can imagine. Breaking down all these covalent bonds to get a reaction going is going to be nigh to impossible, and a good thermal conductor. Due to its hardness, cubic boron nitride, a bit like little pieces of diamond, tend to be used in cutting tools and abrasive components. Now, hexagonal boron nitride is a very different structure indeed, and what we have here is a flat layer of hexagonal rings, as the name suggests. So each ring would consist of 3 borons, shown here in pink, and 3 nitrogens, shown here in blue. Now the bonding here again consists of covalent bonds, which I've shown again in blue, but this time the red bond I've shown here is a pi bond. So each atom forms 3 sigma covalent bonds and 1 pi bond in a flat trigonal planar arrangement. Now it might be worth us at this stage just pausing a second to remind ourselves of how a pi bond works. So if we go back to our year 12 knowledge of pi bonds, so the simplest compound containing a pi bond would be ethene. So if we try and remind ourselves of how ethene bonds, so ethene is C2H4, so we're going to draw a carbon bonded to another carbon, and then we would have hydrogen here, and the hydrogen going back here, and a hydrogen over here, and a hydrogen going backwards here. So all the bonds I've shown here now so far would be referred to as sigma covalent bonds. However, there's a second bond, and if you remember, that's formed because we've got p orbitals here which have got 1 electron each in them, and we can get these p orbitals to overlap with each other. So if we show this, we can show this overlapping here and here, depending on where the electron is, and this is how we get our pi bond. So this is our pi bond. So that's all stuff that you've done previously looking at the bonding in ethene. Now, The bonding in boron nitride is similar but slightly different to this. So if we think about what's going on with boron nitride, so let's think about the boron. It's going to form 3 covalent bonds because that's all it can do. It's in group 3. And nitrogen will also form 3 covalent bonds, but nitrogen has a lone pair of electrons, which it's not using for bonding at the moment. And boron has an empty p orbital. If you remember our work on electron arrangements in our earlier video, we remember that boron is electron deficient. So in this situation at the moment, boron's forming 3 covalent bonds. It's only got 6 electrons in its outer shell. It's not obeying our octet rule. But what we can do here now is, because nitrogen has a lone pair of electrons that it's not doing anything with, we can form a pi bond here. So this is a bit of a weird pi bond, because instead of having 1 electron in a p orbital on carbon and 1 electron in another p orbital of carbon, and those p orbitals overlapping, pairing up those electrons, this is almost like now sort of a coordinates pi bond, where both electrons in the pi bond are coming from the nitrogen. So here's our pi bond, and here's our sigma bond. So this is the situation we have in hexagonal boron nitride, where this pi bond, the one I've shown in red here, has both electrons coming from the nitrogen. So it's almost like a coordinates pi bond. It's all a bit strange. Now, to add to the somewhat strangeness of this, if we go back to our drawing again now, nitrogen is more electronegative than boron. So we would have a delta minus on the nitrogen and a delta plus on the boron. We've got a dipole moment here. So if we think about how these electrons are being shared, there's going to be more electron density around the nitrogen. So it's not an equal sharing of those electrons. We don't have this situation in carbon, obviously, because the 2 atoms are going to be of the same electronegativity, both being carbon atoms. So as it's more electronegative than boron, a dipole moment exists in the boron-nitrogen bond, which is why I've shown each blue atom here with delta minus and each pink one as delta plus. Unlike graphite, hexagonal boron nitride is an insulator. Now, what graphite is able to do, because the p orbitals are overlapping and everything's shared equally, these electrons in graphite would be delocalized completely and able to conduct electricity. In boron nitride, however, because the electrons tend to stay closer to the nitrogens than they do the borons, they're not able to delocalize in the same way as they can in graphite, and as a result, boron nitride is rubbish at conducting electricity. In fact, it's an electrical insulator, which is at a marked difference to graphite, which is an excellent conductor. And this is a common question that comes up in the exam papers for us. Why is boron nitride different in its electrical conductivity to graphite? And this is the reason. It's an insulator because nitrogen is more electronegative than boron, and so we can't get the electrons delocalizing in the same way as we can in graphite. In a similar way to graphite, however, we've got layers here, and we've got weak van der Waals forces between the layers, and they tend to be equally as slippery. What is different between the layers, however, is that in graphite, each layer will stack upon each other so that each carbon is staggered compared to its neighbor in a layer beneath it or above. However, with boron nitride, we tend to get the boron atoms lying directly above a nitrogen atom. So I'll try and show you what I mean by that with a rubbish drawing again. So if we try and draw some hexagons here, there we go, draw a few hexagons. This would be a layer of carbon atoms in graphite, say. Now, keep in mind this carbon here, and I'll just draw like a dotted line beneath it. Now, it would be directly above the hole, if you like, in a hexagon beneath it. Okay, so that carbon atom there would be in that directly above the hole in the hexagon. So we have the layers in graphite are staggered compared to each other. However, in boron nitride, draw boron here, nitrogen, nitrogen, boron, boron, and a nitrogen. There's one ring. And obviously you'd have the bonds coming off there, here. Now this boron here is going to be directly above the nitrogen in the ring below. Borons, nitrogens. Now the reason for this is delta minus and this is delta plus. So the layers are going to arrange themselves so that there is some kind of attraction between the dipoles in between the layers, which may suggest that the bonding in between the layers in boron nitride is not quite as weak as it is in graphite. And in fact, we do see that hexagonal boron nitride is not quite as slippy and as good a lubricant as graphite tends to be. So there we go. The two allotropic forms of boron nitride. Hexagonal boron nitride, similar to graphite. Cubic boron nitride, similar to diamond. Quite complex structures, quite a lot going on there, and they are common exam questions. So you need to familiarize yourself with these two structures, fill in your booklet, make sure that you can then have a go at some questions, and that you can cope with these questions if you were to happen in an exam.